And now it's time for our special guest. Today this is Dr. John Charles. John is the chief scientist of NASA's Human Research Program with the goal of reducing risk for astronauts for deep space exploration missions. Dr. Charles, welcome to the Weekly Space Hangout.
Well, I'm delighted to be here. Thanks for inviting me.
So for that was a really cool title, and can you give some more detail about sort of who you are and what you do?
Well, I work for NASA. I'm a civil servant at NASA. I've been here for since 83, so I've been here longer than many of your listeners have been around. But our job in the Human Research Program here at the Johnson Space Center is to understand the medical aspects of long duration space flight beyond low Earth orbit. And whenever I say those words, that means going to Mars, with stops perhaps at the moon or an asteroid. But our ultimate goal, at least our stretch goal currently, is going to Mars. There are a bunch of risks, human risks, that we've identified between us and Mars, between now and there and then. And our goal is to understand what those risks are and what needs to be done biomedically to reduce those to an acceptable level, and then to implement those changes as much as possible. So I like to say that people going to Mars. That's our whole charter. That's our laser-like focus right now.
Well, I'm going to hold up a book here, which is the new book from Scott Kelly, Endurance: A Year in
Yep.
Space, A Lifetime of Discovery. I haven't actually fully read it yet, but so you worked on this project, right? Finding out
That's
how Scott did in space after a year.
That's correct. I was the chief scientist for that year-long expedition of Scott Kelly and his Russian counterpart, Mikhail Kornienko. I actually got to see my one and only Soyuz launch in March of 2015 when I was in Baikonur, Kazakhstan, watching Scott and Mikhail and Gennady Padalka launch from the Baikonur Cosmodrome. I like to say it's my first and last trip to Kazakhstan. It's less convenient to go there than it is to go someplace else like Cape Canaveral.
Right. Now we know that that Scott experienced quite some dramatic changes to his body, spending a year in the microgravity of low Earth orbit. How from a scientific standpoint, sort of how did he come back?
Well, he came back in remarkably good shape, and seems to have had a few problems after he returned. But his immediate post-flight performance was really not any different than we've seen in other astronauts that have flown 6 months in orbit. And that really was the purpose of his expedition, was to see whether we think we're as smart as we think we are, whether we've learned what we think we need to learn from the 6 month missions to successfully predict what will happen on longer missions. And the reason I say that is because a Mars mission will probably be on the order of 1,000 days, let's say 2.5 years, roughly 6 months to get there, roughly 6 months to get back, and roughly 18 months on or near Mars. We will probably not see any 2.5 year human space flights before the first 2.5 year Mars trip. There's just not enough 2.5 year times between now and then, essentially between now and the end of the space station, to do it more than once or twice. And in biology, I don't know how many of your listeners are biologists, but those that are will understand the term biological variability. And we like to have multiple repetitions in test subjects and astronauts and specimens, so we can see what is the effect of the environment that we're inducing on the physiological parameters of interest, and how much of it is just that person or that rodent having a bad day or a bad year. So we will probably be making the longest flights the first time we send people to Mars. But gee, wouldn't it be nice if we could predict what the outcomes are going to be from space station missions of 6 months or say a year, and then extrapolate outward? Scott Kelly and Mikhail Kornienko were our first chance in this century to make those extrapolations, and so far, fingers crossed, the trend seems to be good.
Now, the environment in low Earth orbit is very different from the environment outside of the Earth's protective magnetosphere. What kinds of additional dangers beyond microgravity are they going to be facing further out in deep space?
Well, you're right. The once you leave Earth's magnetosphere, and that's about, I think, about 6 Earth radii out, Then you are exposed to everything that the entire universe has to offer in terms of radiation. That would be the galactic cosmic radiation, which is deflected by Earth's magnetic field and shields. We are shielded from in low Earth orbit by the bulk, by the mass of the Earth. You're also exposed to the solar particles and the sun's protons and electrons, solar flares, magnetically charged particles that come from the sun. So you are essentially in deep space en route to the moon. That is the biggest difference. The difference that attracted me to this kind of research originally, of course, is the weightlessness or the microgravity. I'm fascinated by the absence of gravity since that's so hard to achieve here on the Earth. But other things to worry about are, of course, the distance from the Earth, the isolation, the confinement inside of a very small vehicle, the total autonomy. The crew will have to be largely autonomous. That means the 4 people that go to Mars, and yes, the crew size looks like it'll be about 4 based on current planning, will have to have all of the skills they need to survive for at least 40 minutes between the time they call for help and the time the help arrives via radio. Uh, the
Right. So the help that they can count on is someone giving them some instructions.
Yeah, look in
Yeah.
the back of the manual. Essentially, that's where the
Right.
answer for your question is. So they will be highly autonomous. Luckily, the vehicle will probably be sort of like HAL was in 2001 without the homicidal tendencies, we hope. And we'll be able to provide a lot of signal conditioning and a lot of just-in-time training and information that's available and needed, available when needed. But in the medical domain, you'd really not like to have somebody reading the directions to you while you're doing the surgery.
Yeah, exactly. Uh, Now, so then let's talk about what kinds of tests you can do to expand human capability, right? Or expand the capability. So, I mean, we now know, and we've kind of known, you say 6 months, that extrapolates out to a year. You've got a better sense of what that does to the human body. What will be the next tests that will be able to sort of find out what happens in that deeper space environment?
Well, the first step that I hope we see is more year-long missions. And I spoke about biological variability. We'd like to make sure that what we've seen from Scott and from Mikhail, is really human performance and not just the the quirkiness of Scott and Mikhail. And if you know Scott or Mikhail or both, you know that they're as quirky as the rest of us. In fact, in some regards, Mikhail was the opposite of Scott. So, do we take the average of the two as the typical astronaut? Well, we'd like to know statistically, what do astronauts really look like? So, we're hoping to fly five more year-long expeditions in low Earth orbit on the space station before the space station is brought to a graceful conclusion, probably in 2024 or maybe as late as 2028. Nobody else has agreed to that yet, but the Human Research Program has that requirement out there and it's being evaluated. So that's our next step. And the next step will involve year-long missions, we hope, plus the 6-month missions that host them, plus the vehicle exchange missions, because a year-long flight will require somebody landing in the old transport vehicle and bringing up a fresh one. We hope the crews that bring up the fresh ones and bring down the old one will be available to us as well for some short flight duration measurements, maybe 6 weeks, maybe 2 months, to give us 3 points in a curve that will then allow us to extrapolate with some certainty out to 2.5 years. After that, though, it gets kind of fun because about 9 months ago, in March of this year, William Gerstenmaier, who was our associate administrator for human explorations and operations, which is our space flight directorate at headquarters, laid out a plan of cislunar habitation. That is, building a miniature space station, really just 1 or 2 modules uh, at the moon. And I'm not on the moon and not orbiting the moon, but in what they call a near rectilinear halo orbit, which implies it's at one of the Lagrange points. The near rectilinear part implies that the orbit is sort of straight line at some points in its curve, making it easier to rendezvous with the miniature space station. While that is being built, the expectation is astronauts will be there for up to 6 weeks at a time, which sort of dovetails nicely with our hope for short duration crews that are visiting the space station and exchanging the vehicles for the long duration crews. And then the graduation ceremony for the cislunar habitat is currently proposed to be a couple of 1-year missions in deep space. And those 1-year missions will actually be testing out what might be the second generation of one of these deep space habitats, which are currently called the Deep Space Gateway. The block two of that might be what's called a deep space transport. And Mr. Gerstenmaier has proposed no fooling sending that to Mars from lunar orbit or from the cislunar environs. So potentially by the earliest of the 2030s, we will see 4 people setting out on a flyby or perhaps a Mars orbit mission. That sounds like a really, really long way away. That is 13 years. That's twice as long as the Apollo program lasted. And yes, that's 3 times longer than the entire Project Mercury program lasted, but this is a different time. But the interesting thing to remember here is that we are already within a couple of years of having to deliver our standards, our requirements for that vehicle. So instead of thinking of it as 20 years away or 15 years away, think of it as, oh my God, our time is up to make a difference in designing that vehicle. Because if that program is approved and if it follows the schedule that Mr. Gerstenmaier outlined, and so far nobody has told us it won't, then we have to finish up our research in the very near term and write the letters, or write the reports rather, that tell program managers how to build their spaceship to send astronauts to Mars. So that's why it's really interesting and really getting to be a fast-paced program, despite it seeming to have a long lag.
No, absolutely. I mean, early 2030s sounds like right around the corner when you think of all of the different pieces of hardware that need to be created and implemented. I'd like to talk just about, you mentioned, this trip of going to Mars. It's on the order of 1,000 days. It is months of travel there, months of travel back. Ideally, months spent on the surface of Mars to explore and do the science, if it is an actual human mission. And I know that extends beyond NASA's sort of existing radiation load that they're willing to let their astronauts have. How much more of a load do you think that the astronauts are going to be handling doing a much longer duration trip like this?
Well, the radiation environment in transit will be approximately 10 times what it is in low Earth orbit. And in low Earth orbit, it's approximately 10 times what it is here on the surface. Those are thumbnail numbers that they let me say out loud, because once they start explaining, well, it's the different species and the different linear energy transfers and all that kind of stuff, and radiation is not really the same as radiation. There's different kinds and different flavors, and different times of the solar cycle you have different radiation environments. But John, for your purposes, just tell people that low Earth orbit is 10 times higher than surface of the Earth, and transit to Mars is 10 times higher than low Earth orbit. And being on Mars is 10 times less than that, which is equivalent roughly to being in low Earth orbit. And that's been documented by in situ measurements. The composition of the radiation will be different depending on, like I said, what phase of the solar cycle and where you are and what the sun chooses to throw at you. The question then is how much risk are we willing to accept to expose astronauts to that environment? The current guideline is that they should be exposed to radiation that does not cause more than a 3% increase in the risk of exposure-induced death. That's REID, R-E-I-D, risk of exposure-induced death, over their lifetimes. So that is really what's driving our research, to understand what that radiation dose really translates to and how can we shield against that. Bear in mind that risk, and that is the largest radiation risk that has been associated with this kind of exploration class mission, only becomes manifest long after the mission is over. That's a lifetime risk of exposure-induced death. So if we're talking about going to Mars in, say, 15 years or 20 years, and then a mission that lasts 1,000 days, and then the astronauts having an increased risk of lifetime risk of cancer, we're talking about cancer which may not manifest for 30 or 40 or 50 years from now. Look how fast progress has been made in cancer treatment over the last 30 or 40 or 50 years and tell me that we probably aren't seeing something similar in the future, suddenly we can start negotiating and says, okay, maybe we can accept a slightly higher risk of cancer because by the time the cancer becomes manifest, we will probably have better ways to deal with it
Hmm.
back here on the Earth. So I'm not talking. NASA does not have the charter of putting people on Mars and leaving them there. The Martian notwithstanding, Mark Watney was, that was an accident. We never meant for that to happen. But and we're not about colonizing. That's Elon Musk. That's not our thing. That's Musk's thing. So we're talking about sending people there, having them do an extremely difficult job for a really long time, being successful and coming back and then living the rest of their lives in good health as much as we can make it possible. So those are the kinds of questions, the kind of discussions that we are having no fooling right now every day, trying to understand what the right way to do this is.
Now, you just mentioned briefly about Elon Musk, but he's not the only one who wants to colonize Mars, and of course, Mars has what 30%, 35% the gravity of Earth.
Yeah,
The
38%.
yeah, the Moon has 15% the gravity
Yeah.
of Earth. Do
Yeah.
we know if a human being can live out a lifetime on that kind of gravity?
We do not know that from having demonstrated it in any biological system whatsoever. However, I am not concerned about an astronaut or a person living out a lifetime. The concern we have is not the accommodation to the low gravity environment. It's what if you were so foolish as to want to come back to a high gravity environment afterwards? That's where our treatments and our research and our countermeasures are focused. It's easy to live in low gravity, and uh, Wally notwithstanding, I sincerely doubt that your bones will dissolve in weightlessness. Even people here on the Earth who are quadriplegics through trauma and accident don't seem to get much less than about 60% of their bone mass, over the course of a lifetime. So I'm guessing, without data, that astronauts will be able to retain roughly 60% of their bone mass, even if they spend years in weightlessness. And at 60%, you're still not at a really high fracture risk. So the idea of bones dissolving and the idea of a single step back on Earth causing massive fracturing, those are tropes of science fiction. That's really not what happens in biology, as far as I understand. But we do have to worry about the adaptations to weightlessness, like the fact that the calcium that comes out of the bones may end up in the urinary bladder or in the kidney and cause kidney stones and things like that. So there are secondary effects that may make people less comfortable in weightlessness than they deserve to be.
Right. I mean, it feels to me like it is a risk, is an experiment of sort of an unprecedented, unknown outcome to spend potentially. What if people have children in that low gravity environment, and if those children grow up? I mean, you have lots of people who would volunteer to go and colonize Mars, but what you just said, right? Like, would you be willing to suffer horrendous kidney stones nonstop for that opportunity?
Well,
I think
probably
it's
wouldn't
a
be nonstop.
well, sure, yeah,
Let's
horrendous
say,
kidney stones. Anyone who's experienced a kidney stone
yeah,
has said they're no fun. They're no
yeah, I've had a
picnic.
kidney stone, so
Yeah,
I agree.
yeah, they're no joke. So
They're no joke.
yeah, and so
But
it feels to me like there are what NASA is doing to send human beings there, some kind of rotating space station that can give us like longer idea of what this lower gravity is. It feels like to me that this reduced gravity for long duration human spaceflight is the big unknown.
yeah, you said a couple of things, Fraser. I want to tag on a few of them. One is people know how not to have babies, so hopefully there won't be any unplanned pregnancies on a Mars mission. If God forbid something like that happens, well, there's going to be lots of splaining to do afterwards.
Well, I'm more talking about the colonists,
Yeah, but
the
see, the
SpaceX
colonists,
colonists.
that's up to
I
SpaceX. Elon
understand
Musk can
that.
fund his research and solve his problems if he insists on sending people to Mars in perpetuity, and that will happen. And I'm guessing that at some point it will happen. And biology having shown it is wonderfully resourceful and flexible, will figure out a way to have healthy young people thriving on Mars. But I guess, like that movie, The Space Between Us, showed, it might be difficult to come back to the Earth. And there's also a book by Robert Heinlein, which was The Moon is a Harsh Mistress, was discussed this back in the 60s. But in terms of fractional gravity, or what we call artificial gravity, which is really pseudogravity caused by rotating vehicles, that was past tense a topic of research within the Human Research Program. And because of right now some budget cuts that we have taken, and also this accelerated schedule that I described earlier, we are discontinuing our research in artificial gravity, except for a few small studies that will use the Japanese centrifuge on the International Space Station with mice, rodents. We are saying, we have been told, hey, look, you guys have been really successful with weightlessness, so let's not embark on an entirely new process of designing brand new technology for brand new spaceships that we can't even imagine, which I will only guarantee they will not look anything like the Hermes in The Martian. They will not be that big and spacious and luxurious with all that empty space on the inside. Like I say, we're talking about, if Mr. Gerstmeyer's plan comes to fruition with sending people to Mars in the early 30s, it will be in a module and something about the size of 2 space station modules. So very, very limited capability, practically no privacy, anything like that. I'm thinking that we're probably going to be okay with weightlessness. If somebody else wants to come along and study artificial gravity, I'll sign up for it, because I think it's the good thing to do. But we are not probably going to have that luxury.
Right. Okay. Well, maybe we'll do a Kickstarter.
Yeah. Right.
Dr. Schultz, thank you so much for joining us today. As you can tell, you were able to answer a bunch of my burning questions, and I really, really appreciate it. And good luck with what you guys are doing. I think, we're reporting on it every week. So the topics that you brought up, everyone is very familiar with what you're talking about, and it is really exciting to sort of hear these next steps that NASA's taking. Mars. It'll be great.
All right, Fraser, thanks very much for the chance. Appreciate talking to you.
All right, take care.
Bye-bye.
All right, so now we're gonna move back. You're free.
Okay,
John.
good.
Thank you so much for joining us, and such great information. I really appreciate it. I apologize to everybody who had a bunch of questions, but he just had such great answers that I just had to go through it. So, all right, let's move on to the actual show now. All right. Here we go. Oh, let me stop the recording of that. Nobody else stop anything. Okay. Welcome to the Weekly Space Hangout for Wednesday, October 25th, 2017. My name is Fraser Kane. I'm the publisher of Universe Today. This week, we're going to be talking about the discovery of a ring around a dwarf planet, more asteroid friends, less asteroid enemies, how neutron star emergence brought us gold, and maybe, just maybe, the discovery of the first interstellar comet. All right, joining me this week, we've got Dr. Morgan Renberg, the Director of Scientific Presentation at the Fort Worth Museum of Science and History. Morgan, welcome.
Hey, Fraser. It's good to be here.
We've got Dr. Kimberly Cartier, Earth and Space Science reporter for EOS Magazine. Kimberly.
Hey, Fraser. Hello, everyone. Happy Wednesday, or whatever day you happen to be listening to this.
And last but not least, Dr. Paul M. Sutter.
You'll get it. You'll get it.
I'll get it. You trained so well. Last but not least, Dr. Paul M. Sutter, an astrophysicist at Ohio State and the host of Ask a Spaceman. Paul.
That's right. Hi, everyone. And you know what? Just happy Wednesday. I don't care about the other days.
But you're not saying hi to all of our podcast viewers who are listening to this on their way to work on Thursday morning?
Right.
Yeah, you should have listened on Wednesday.
Hint, hint.
As if this podcast is done on Thursday morning.
I mean, you can listen to it
Monday morning?
You can have whatever kind of day you want, but I'm only going to wish you a good day.
Well, in that case, happy Friday, everyone.
So before we get into the news, I want to remind everyone that this show is powered by the awesome energy of the Weekly Space Hangout crew. This is, of course, the community of fans and friends who organize to discuss the topics, to propose the stories, to organize the special guests. And by the way, this week's special guest is awesome. So make sure, like, I know you're like, normally you just want to hear us, yak, and then you just skip the special guest, but no. This is a very important special guest. But yeah, they organize a special guest, and you can join this community by going to wshcrew.space. And then just go into the Slack chat and yak with all of us. It's a good time. All right, so we're gonna start. Paul, you've got some updates on the biggest story of the year.
Of the year? Well, hey, the year's not over, man.
The year so far.
We talked about this last week about the formation of elements in the neutron star merger that was recently detected with both gravitational waves and traditional observatories in gamma rays. We saw it in X-rays, radio and infrared and optical, the whole deal. And you brought up this interesting question about where do our heavy elements really come from? Because we've had this story told to us for decades, really ever since the 50s, that heavy elements are born in supernova explosions. So all the elements heavier than iron come out of those massive explosions. But now everyone's saying, no, it's neutron stars this whole time. So we talked about it a little bit, and there have been some papers published about it and some popular articles written about it. And so now I can say for sure what the real answer is.
And the answer is?
Drum roll.
Maybe.
Wow.
That's it. Yeah. Well, we know for sure. One thing that this result did produce is now we know for sure that neutron stars produce elements like gold, because we see the spectrum of gold in the remnants of this explosion. And we estimate this explosion made something like 3 Earths worth of gold. So 3 Earth masses worth of gold, which is a lot of gold.
That's a lot.
That's a lot of gold. But it doesn't mean all the gold in your universe, like all the gold that might be on your ring finger, came from neutron star mergers. Supernova can still generate gold and silver and heavy elements, but supernova detonations are very complicated physical systems, so we haven't really worked out the physics, and the observations are heavily obscured by all the other stuff going on during a supernova explosion, so it's hard to tease out spectral lines from individual elements. So we know neutron stars are producing a lot of heavy elements now, which we guess they were, and we know that supernova are also producing heavy elements. What the balance is of who's producing the most and when and where is still an open question.
So if I'm holding a molecule of gold or an atom of gold in my hand, is there a way to tell, like by isotope or something, whether this is more likely to have been produced by a supernova or a neutron star collision or some other process?
That is a really good question. With just one atom, no, you can't do any statistics or analysis. Gold is gold across the universe. It doesn't matter how it's made, it will look like gold. If you have a lot of gold or a lot of platinum, where you do have some of those more rarer isotopes mixed in, if we knew the detailed physics of neutron star mergers and supernova explosions that would differ in their production rates of various isotopes of gold or platinum or any of the heavy elements, you might be able to make a guess that, the gold on the Earth most likely came from a supernova or most likely came from a neutron star merger. At this stage, it's just a little bit too hazy.
So like 100 years from now, the high rollers are going to be handing out wedding bands of neutron star gold, and the rest of us will swim it with good old
Very
supernova
special
gold.
Exactly. That's exactly right.
What else did we learn from this collision?
Oh, this is something else that we brought up last week, and I kind of went off the cuff. Maybe I went off the handle talking about using neutron stars as what are called standard sirens, or a way of measuring cosmological distances. And a paper has come out using this neutron star merger to give us a value of the Hubble constant. Who knew?
And did it match
What is it?
previous? Does it give us a more accurate measurement of the Hubble constant?
Yeah, no. Their estimate. So current estimates, like some from Planck, the Planck satellite early universe measurements are at 68 plus or minus 0.5 kilometers per second per megaparsec. That's early universe measurements. Late universe measurements from supernova and other is actually higher. If I'm remembering right, it's like 72 plus or minus 2. And so there's some disagreement there, which we're still trying to figure out what the source of that is. That's a very interesting question. The number produced by this gravitational wave result is 70 plus or minus 10. So, okay.
So smack
it's
dab in the middle, but not terribly informative.
Yeah, it's a measurement. They did it, but it's with just one sample. It's not going to be terribly informative.
Right. So if we had never come up with any other way of measuring the Hubble constant and suddenly jumped straight to gravitational wave detections, then this would be the one way to
Then
do
we
it.
would have discovered that we live in an expanding universe.
Right.
Now,
okay.
Paul, is that large uncertainty just because of there's just one event that you're using to get that number? Do you think you mentioned last week that we may end up detecting up to like 10 of these per year, presuming that these instruments keep running? Would that help pin down the number better?
Yeah, that's also a very, very good question. So most cases, the more objects you add into the bucket, the lower your error bars or the smaller your error bars are going to get, unless those error bars aren't coming from statistics, if they're coming from fundamental uncertainties in your measurement process. These are called systematics. If systematics are dominating your uncertainty, if there's just fundamental limitations in the way your instrument is set up or your observing structure or whatever, then you could add 1,000, 100,000 objects and you're not going to bring those error bars any smaller. So I suspect once we get up to 10 or 100 neutron star detections, this standard siren approach will be even better. Whether it will be competitive with things like cosmic microwave background or baryon acoustic oscillations or supernova or any of the other methods we use to measure the Hubble constant, that's an open question.
Arjun is asking in the chat, are supernovae able to make the stuff at the bottom of the periodic table, like uranium and such, in the ratios that we see in the universe? So is it, is there a difference there between the stuff that's sort of closer to the middle as opposed to the stuff at the edges?
No, there are two mechanisms for generating heavier elements: the slow neutron capture process and the rapid neutron capture process. This is S process versus R process, and both can generate a lot of the heavier elements. It seems that the R process, the rapid process, dominates in our universe. So a supernova or a neutron star merger can fill out that periodic table equally well. But I do have to say, I have a mea culpa. From last week, I was making fun of the term kilonova, implying that was incredibly large. Like we went past supernova into hypernova and ultranova or whatever. We went to kilonova. Kilonova's neutron star mergers are much, much weaker than supernova. And they're about 1,000 times brighter than a typical nova, hence 1,000 novas, kilonova, but they're still weaker than supernova.
This is just a week of
they're
your mea
weaker
culpas.
they're weaker in like their light output, right? But their gravitational wave output presumably is higher, or we would be seeing supernova gravitational waves all the time, right?
Unless supernova gravitational waves are the wrong frequency. That is something I don't know off the top of my head. If gravitational waves from supernova could be quote unquote brighter than from neutron star mergers, but if they're at the wrong frequency, they're outside the detectable range of LIGO and Virgo.
Paul,
And so Oh, go ahead, Kimberly.
I was really glad you brought the fact on why it's called kilonova. I always, in astronomy, there are so many names that make no sense whatsoever.
And I just, yeah, you're right. I just assumed it made no
reason
sense.
why it's called kilonova. That makes me feel so much better, actually.
It's 1,000 nova.
It really does.
Oh, there you go. All right, well, let's move on to the next research for the week. Kimberly, what have you got for us?
Yeah, so I have some good news and some better news. The good news is that Earth has a new buddy. Not a new buddy, but a newly found buddy. And the better news is that Earth is less likely to be destroyed by giant asteroids. So, good news and better news this week. So the new buddy we got is an asteroid that orbits the sun, but in such a particular way that it stays near Earth for centuries at a time. And so I've seen it been called Earth's new moon or a quasi-moon. It's not a moon because it doesn't orbit a planet. It's an asteroid that orbits the sun. But the asteroid's orbit, it's tilted and slightly more elliptical in such a way that it stays within between 38 and about 100 times the distance of our primary moon, if you want to call it that. And so it's never going to collide with the Earth, but it's just sort of hanging out there near Earth, and it's sometimes a little bit ahead of us, it's sometimes a little bit behind us, and so it appears to be in orbit around our lovely little planet. And it's just sort of a little quirky thing. It was first detected back in April of last year by an asteroid survey using the Pan-STARRS data, and at first people thought it was just a little bit of space junk, because space is full of junk. And then follow-up measurements actually showed it to be a tiny little asteroid, something like 40 to 100 meters in size. So, fun little friend.
And these happen from time to time. Like there are other quasi-moons that have, and
there was
sometimes
one a few years ago.
Yeah.
Yeah, there was one a few years ago, and it stuck around for about 10 years, and then its orbit naturally took it away from the Earth. This one is a bit different from that in that it's going to stay around for centuries at a time, and it doesn't get any further away than about 100 times the distance between the Earth and the Moon. If it gets out that far, Earth just sort of tugs it back just a little bit, and eventually its orbit will take it in such a way that Earth can't tug it back anymore, and it'll move on its merry way. It'll find some new friends out there, but for now we have a little asteroid companion.
I think you're anthropomorphizing this asteroid too much, Kimberly.
What?
I like it.
Fun.
But now you're about to talk about the killer asteroids. Are they good buddies too?
They get a little bit too close. They're a little bit too friendly with us sometimes, and those are never fun things. But this is sort of, as I was learning more about this, I realized this was actually a little bit of a math story even. A group in California were noticing some discrepancies in our estimates of how many large asteroids we estimate around Earth. Asteroids anything larger than about 1 kilometer in size, which are the ones we really care about because those are the ones that can cause so-called extinction level events. We sort of would like are on potential collision paths with the Earth. That would be a good number to know. And a group in California realized that our current estimates ranged anywhere from like 800 to 1,000 of these kilometer-sized asteroids, and that's a pretty big range. That means that we either have found something like 75% of them or anywhere closer to like 95. And that's not good enough for public safety. And so they took a closer look at the math and the statistics, and they realized that there is a flaw in how we estimate the sizes of the asteroids. And going a little bit off on a tangent, how we actually get sizes for most asteroids is not by physically measuring the size or doing some sort of parallax or angular type of estimate of the size, but we use the brightness of the asteroid or the albedo of the asteroid as a proxy for the size. So we see how much light the asteroid's reflecting back, and we say, oh, it must be such and such size. But there's a fundamental flaw in that asteroids can either be, if it's faint, it could be far away, but big and bright, and it's just dim because it's so far, Or if it's faint, it's because it's not reflecting a lot of light, no matter how big and close it is. So when we do that sort of proxy measurement of size, we group asteroids together into size categories, sort of to take care of that bit of uncertainty. But there's been no consistent way on how we group sizes together, and so there's been no consensus of how many of these big guys there are, because no one's grouping them the same. Apparently, when you take care of that, we find out that there are actually fewer of these large kilometer-sized asteroids than we first suspected. The number is closer to about 930 or so, which means we actually are 37 or so kilometer-sized asteroids, which is not so bad. We're pretty close.
It's too bad that we are not still engaged in a mission to send asteroids, or to send astronauts out to collect a nearby Earth asteroid
it would be
and bring
really
it back
nice
to Earth
if
orbit.
we had one of those missions on the table, but we don't.
Sounds like we have a good target now.
Maybe we know for sure how far away it is.
No.
Because we put it in this. Never mind.
Yeah.
Well,
Bad. We'll just have to wait for Osiris-Rex to come back.
yeah.
There is that.
Like,
And there are plenty of private groups that are looking to send send missions to asteroids to find out more about them. There's the Space Guard group, and
in a century or two they might be ready to do it too.
And
the timing is all ready.
612 Foundation, 512 Foundation, I forget which one it is. So there's a few people who are looking to do this, and then of course there's the people who want to mine them for their precious neutron star gold.
Right. Yeah.
Or just go right to the source, go straight to a neutron star.
That is not what I want to do with my weekend.
You get 3 Earths worth of gold.
3 whole Earths. Where would you even put that much gold?
In my face.
I would put it on Earth. I would make a new Earth made out of gold.
Yeah.
Maybe that's
the
what
ultimate
Planet
Midas.
Nine is.
Yes.
I got a question from Arjone. Do things get stuck on our L4, L5 points like Jupiter? Do we have Trojan asteroids?
I'm not 100% sure. I mean, there are plenty of them, but I don't know.
I think the answer is yes.
Probably.
I think the answer is yes. They're pretty small, and yeah, I think the answer is basically yes. They're relatively small, and hopefully JWST doesn't run into any of them.
Oh, well, no, but that's at the JWST is going to the L2 point.
Yeah, no, they wouldn't collect at L2.
No, but yeah, and at L4, L5. All right, Morgan, you're on my screen right now. Why don't you bring us up to date on a dwarf planet with a ring?
Back in the good old days, when spacecraft were spacecraft and we were going to the moon, only planets were allowed to have rings. But our standards have been slipping, and we now know that all kinds of objects can have rings. From maybe asteroids to the first sort of trans-Neptunian object that we found with rings named Chariklo. And now we have evidence that a Kuiper Belt object or a trans-Neptunian object, depending on sort of how finely you want to split hairs, also has a ring system. This is the minor planet Haumea, which is actually a pretty substantial object. We're talking about something about 800 kilometers across. That's orbiting a little bit beyond the orbit of Neptune, but it's on a pretty eccentric orbit, so it actually sort of dips inside of Neptune sometimes and then sort of heads all the way out towards the outer reaches of the Kuiper Belt at other times. And so we found this ring system using the same technique we've used to find basically all the other ring systems around bodies smaller than planets, and that's by doing occultations. So a bunch of astronomers distributed across the world watched a star as it passed behind Haumea. And they actually weren't even trying to find rings. These things, stellar occultations are really useful for teaching you things like exactly how big the object is. So if we want to know to a decimal point how big across it is, occultation is the best way to do that. Occultations are the first way we realized that Pluto might have an atmosphere. Now that we know Pluto can have an atmosphere, we're interested in whether other similar objects might have atmospheres. And so if there's an atmosphere, it blocks a little bit of that star's light, as it passes near the surface, and you can calculate the density of the atmosphere. But what they saw instead was that about 1,500 kilometers from the center of Haumea, the light blinked out. And then after a second or two, it blinked back in. And if just that happened once, you wouldn't be surprised. But all these telescopes noticed this happening. And they didn't notice it just happening once. They noticed it happening twice, once it had crossed over to the other side of Haumea as well. And this is a classic sign for what a ring looks like. And they were able, by the duration of the time that the light blinked out, they were able to calculate that these rings were about 75 or 70 kilometers wide, which is a pretty reasonable size ring, much larger than the rings, for example, that we saw around Chariklo. But the big question that this opens up, not just for Haumea, but across all these small ring systems, is why we're seeing them at all. Because there's a lot of forces at work to sort of destroy ring systems. The solar wind can kind of just push them away if they're held by a relatively small object. They can clump back up into an object. You know, the Earth used to have a ring system, but then we got the moon. And gravitational perturbations can sort of just diffuse the ring away. There's a lot of reasons rings should be gone. There are not very many reasons that rings should exist. Mainly, we think they happen on these small objects because of collisions. Either, it had moons and those moons collided, or an asteroid hit the surface of Haumea and knocked up a bunch of material and created a ring. And most of those kinds of collisions were probably happening hundreds of millions or billions of years ago, much, much, much longer ago than the ring should have survived. And so that either means we don't understand the processes that are creating these rings, or lots of things have rings over the course of their lives, and any given ring system is only there for a relatively short period of time. But because there's a gazillion objects to look at, if we look at enough, we're always going to catch that one lucky collision that led to the ring system that we're able to see.
But very different. Go ahead, Kimberly.
So dwarf planets can have rings, and giant planets can have rings, and we see them all over the place in our solar system. But terrestrial planets don't have rings? And if not, why not? I want
There's
one.
probably
the homework question.
Yeah, there's probably not one simple answer. You get close enough. For example, Mercury. Mercury's had the crap battered out of it over the course of the solar system, but it's so close to the sun that the solar wind is probably too strong to allow for a ring to form. Earth had a ring, like I mentioned, when a protoplanet struck it early in the solar system's history, but that knocked up so much material relative to the size of the Earth that gravity was able to sort of clump that back together into an object whose gravity was then able to sweep up the rest of the material.
Yeah, isn't a ring an indication of a really bad day? I mean,
someone had a bad day if you see a ring, because material doesn't just sort of float around in space ring formed. That's all a solid object once upon a time. And, we think Saturn's rings might have formed by a moon falling close to Saturn and sort of getting torn apart by Saturn's gravity. We think the moons, or some of the rings, for example, of Jupiter or Neptune, happened because of these sort of constant micrometeoroid pelting of moons, knocks free a bunch of material. Other rings we think probably happened because of some cataclysmic collision between one or more moons. So something went boom basically every time you have a ring system.
Yeah, like won't Phobos, Phobos is spiraling inward to Mars, and in 50 million years or so, it's going to get torn apart when it enters the Roche limit and get turned into a ring. But a ring is not this sort of beautiful thing to wonder at. It's time to build a bunker. When you see a ring, it's time to build a bunker.
I think it's too late. I think it's too late.
It's too late to build a bunker. Yeah.
I should mention too that we see ring systems around exoplanets as well. The ones we're seeing now are like stupendously large, because everything that we see with exoplanets is really big because that's what's easy to see. But there's nothing about ring systems that are unique to our solar system. And we're starting to see them more and more places around the galaxy. And we ought to imagine that every star system probably has rings in it, one place or another.
All right, so my news for this week is, so apparently it's a very, Morgan was quite impressed or confused at my journalistic integrity. I'm not sure. So there was a really interesting announcement that came out of the Minor Planet Center today, and this was a comet that was on a really strange orbit. And if the following up observations turn out to be true, this is possibly the first interstellar comet that's ever been seen. So the comet is called C 2017 U1 Pan-STARRS. Of course, it was discovered with the Pan-STARRS, which we mentioned earlier. And it turned up this comet, I guess a couple of weeks ago. And typically the orbit of these comets is, they measure the eccentricity of the comet. If it's 0, then it's perfectly circular. If it's, 1, that's a parabola, sort of a perfect parabola. This is on a hyperbolic trajectory, so it's actually 1.2, which is the sort of the highest eccentricity that's ever been seen. But right now, nobody's really entirely sure if that's what it is, and the Minor Planet Center is asking for additional observations. One of the things that's quite interesting is that it sort of came out of the direction of the constellation of Lyra, and there's the star Vega is in that direction, and so it's possible that some great simulations that have showed this comet sort of spiraling out of Lyra towards us as the Earth is moving around the sun year after year. So obviously it's very highly unlikely that it actually originated from Vega, but still, it is, I guess, expected that these things are out there, that there are these interactions between the Oort clouds of different star systems as they pass one another. And so just the possibility that we actually found one is kind of mind-bending.
Yeah, this shouldn't surprise us too much. Some sort of simulations of how solar systems form suggest that our Oort cloud basically stretches halfway to the distance of the next star. And if Proxima Centauri's Oort cloud is also stretching that far, then they're in contact. And some of these models try to simulate that and suggest that as much as 10% of our Oort cloud might have come from other star systems. That being said, there are ways to take comets from our solar system and put them on hyperbolic orbits. And so it's easy to get ourselves all excited about an extraterrestrial comet, but really this is a comet that just had a close encounter with a giant planet, for example. We didn't notice it before, but that giant planet encounter bent it onto what looks to us like a hyperbolic orbit, even though it really had been in the Oort cloud, since the beginning of the solar system.
Yeah, and it made its closest approach to the sun back on, I think, the 9th of September. And so it was only discovered a month after it had already made that close encounter and is well on its way to heading back out into deep space. And it's gone. It is going faster pretty much than anything else we'll ever see. It's quite amazing how fast this object is going. And like I said, there's some great simulations that show its speed. So that's it. I get to present that kind of news because I have no scientific credibility.
So it could be an interstellar.
It could be. Scientists
totally
say
could be.
maybe.
Totally could be.
Yeah.
So
and if it is,
rocky things.
If it were an interstellar, say we were know for sure it was interstellar, what would we learn from that fact?
Well, one of the cool things that we would be, if we could, say, scoop it up and study it in detail, we could see how the elements in another star system were distributed. Because a lot of assumptions that we make about the age of our solar system, the relative age of certain things in our solar system, comes from what we think the distribution of elements when the solar system was forming looked like. And we've only studied in detail one solar system. If we could get a sample of another solar system and it also showed calcium, aluminum inclusions in its rocks, that would tell us something about the conditions that star system formed under and whether that looked like or not like our own star system did 4.5 billion years ago.
I mean, if you could take a sample of it, you would know instantaneously that it did come from that it didn't come from the solar system, right?
Oh, absolutely. It would be unambiguous. If you had a comet-sized thing that you could sample, it would be unambiguous that it came from another solar system. It's just a question of how different or similar that solar system looked to us, because it would absolutely be a little bit different.
Amazing. All right, well, now it's time for our guest. And then, of course, this is where the guest is. I'm going to tell Chad that it's happening at 55:43 in my recording.
Star date.
Yeah. And now it's time for us to wrap up the show. Now we've been waiting to hear about some suggestions on how we should wrap up this show. So far, you're gonna have to just keep dealing with us, just blindly trying to figure this out.
But
so Morgan
has any good ideas?
Yeah. So
sorry, folks.
Okay, so Morgan, you had an idea this week.
I did have an idea. I'm not sure I'd call it a good idea, but this week, before our next show is Halloween, and I'm a very strict holiday person in that once the holiday is over, you can no longer talk about it. And so this is our one and only opportunity to talk about Halloween. And so my question to everyone is, what solar system hellscape would host the best haunted house come Halloween? And I'll lead off just to give you a moment to think. And my choice is Saturn's moon Hyperion, because it's one of the very few objects in the solar system that tumbles chaotically. And so on any given moment, you wouldn't be able to predict whether it was going to be day or night 10 minutes later. And so if the zombie horde was approaching, the lights could just suddenly all go out. Its gravity is also extremely low. And so things could be sort of coming at you from all directions, and bam, it's suddenly night, and you weren't prepared for that.
So really, you suggested this idea so that you could sneak in a little discussion of Hyperion.
Best moon ever.
Best moon ever.
Yeah. Well, I would say, if you were on Pluto and you were tidally locked to Charon, you just always have moon in the sky all the time. And if you're on Charon, you'd have the Pluto in the sky all the time, and that's just like a mainstay of your Halloween view.
Infinite werewolves.
Infinite werewolves.
It's always a full moon.
It's always it's not necessarily always a full
bad
moon, but you'll always have the moon anyway. But yeah, boy, infinite werewolves. Oh, that would be trouble.
So I'm gonna say that I really dislike haunted houses.
Oh.
And things popping out at me. I'm not a really traumatic childhood experiences with haunted
every
houses.
solar system body is a hellscape to Kimberly.
Yeah. I'm gonna go with the depths of Europa's oceans. Dark and turbulent, and possibly filled with space whales.
Yes.
I can sneak up on you in the dark.
They're very quiet.
Yes.
Because they don't have eyes.
Yeah.
Yeah, that's how it works.
Yeah.
All the whales in my nightmares don't have eyes.
So that was really uninspiring, but that would honestly be a scary haunted house for me. So yeah.
Paul?
I pick Earth because it's the only planet with ghosts and vampires.
That's the only
that we know of.
Well, the only place that has human blood is Earth.
So far.
Well,
therefore, the only place that can have vampires is
you know what? Morgan's Hyperion zombies don't have any human brains to eat.
Hey, I've got a question. How far out in the solar system does solar output have to be low enough where vampires can exist during the day? Like, is Mars awake? Can Mars support Vampires?
Depends on what canon
How-
you use.
Yeah.
How close to twilight the time of day,
Thank you.
can vampires survive? You know, because you get to Saturn and light is 1% as bright.
Okay, so
as
we
it
can
is on
we
the-
can measure this
on Earth.
and extrapolate out. Okay.
But it depends on which one you're going for, right? Like if it's on Preacher, right, the vampire in that show, he can sort of be outside in the direct sunlight, but with like a robe on.
There's so much uncertainty.
Yeah, well,
I'll
others
let my
just
grad students work on it.
yeah. There's
It's
some math
Buffy
involved.
style. I don't know.
All right, let's wrap things up. So, thanks to our special guest. Thanks to my co-host. Thanks as always to everyone from the WSH crew for helping out with the show. Thanks to all the viewers. And we'll see you all next week after the scary Halloween is past.
Thank you.
Thank you.
Bye.